All right, so now we're going to be looking at chapter 8.2, which is the reciprocal function family. Now, to review a little bit of what you already know, you've seen this form of equation quite a bit in the past. So here we have the general or the vertex form of an absolute value, the general or vertex form of a quadratic, of a radical, of an exponential, and then today we're going to be looking at the reciprocal function family, which is basically our rational version of all of this. So you know that the graph that you get for this is a V shape, the graph that you get for this is a U shape, the graph for this looks like that. Now if we make this plus or minus, then it would look like that. So it's basically just a parabola or a quadratic that's been flipped on its side. Then for this one, we get a graph that looks like that. Now when we're doing the graph of this rational function, what we're going to end up with is something that looks to the effect of this. So there's going to be two sides to it, and then you're going to have, just like you had with exponential functions, you're going to have horizontal and vertical asymptotes. So we're going to look at how do you figure out what is the movement of this entire thing, as well as what, which quadrants are these going to be located in, and then also what is the stretch, compress, and reflect going to be based off of all of the information that we've got. So just to, again, review a little bit more, remember that your A value is going to be your stretch, compress, and reflect. So if it's a negative, it's going to be a reflection. So this, instead of being in the first and third quadrant, will be in the second and fourth. If it is above 1, if the absolute value is above 1, then it's going to be a stretch. If the absolute value is below 1, it's going to be a compression. The opposite of your H value is your horizontal movement. So if this were x minus 3, then that would mean you would move 3 to the right. Then your K value is your vertical movement. So if this is plus 5, then it would be 5 up. Instead of having a vertex, what we're going to do is we're going to move the intersection of the asymptotes is going to be what we move up and down, left and right, based on your H and your K values. And that's about it. Before we go into problem number 1 and graph y equals 8 over x, when x does not equal 0, we're going to take a look at the parent function first. And the parent function for a rational function is y equals 1 over x. So in order to be able to graph this, we need to make a set of a table of values. And my recommendation is that whenever you're doing a rational function, to have at least 8 x values so that you can get the shape of the graph. Because what we're going to end up with normally is a graph in what I would call the first quadrant and a graph in the third quadrant. Or if it's a reflection, you're going to end up with one in the second quadrant and one in the fourth quadrant. So having 8 points gives you enough points to be able to show the curve on both sides. We are also going to have asymptotes on this. We're going to have a horizontal asymptote, which is going to be here. On the parent function, it's just simply the x-axis. We're also going to have a vertical asymptote. And on the parent function, it's going to be the y-axis. Now, what's going to happen is that those asymptotes are going to move left and right and up and down based on the h and the k values that you're given in your equation. So let's take a look at the values that I chose in order to be able to graph this. What I did was I went with 1/2, 1, 2, 4, negative 1/2, negative 1, negative 2, and negative 4. And the reason why I did 1/2 and negative 1/2 is because what's going to happen with your graph is it's going to get closer and closer and closer to that asymptote as it goes both up and down. So you really need to have some sort of fraction in there to be able to show that it's getting very, very close to that asymptote. Then I did 1, 2, and 4 just to show that curve and also to show the curve going towards that horizontal asymptote as well. When you come up with this table of values, this is the graph that you get for y equals 1 over x. Now for y equals 8 over x, what we should expect, since that 8 is in the A position, we should expect to see a stretch. Now, what that means exactly, we'll find out once we go to graph it. We're going to see does that 8, does it make it go towards the origin, or does it make it pull away from the origin? Okay. So what I want to do again is choose 4 values on one side of the asymptote and 4 values on the other side of the asymptote. So I'm going to go with, again, 1/2, 1, 2, and 4, and I'll see what exactly that does for us. So 1/2, and then 1, 2, and 4, and then -1/2, -1, 2, and 4. So there's only really one thing that I have to work out here that's going to be difficult, and that's going to be, I'm going to get a complex fraction when I substitute in 1/2 for x. So I get 8 over 1/2, which is the same thing again as saying we've got 8 over 1 divided by 1/2. So let's go ahead and instead of trying to do this vertically like this as a complex fraction, let's go ahead and change it into a horizontal problem, which is what you're more used to doing with these fractions. So we get 8 over 1 divided by 1/2. Well, you all should know that that's 8 over 1 times 2 over 1. So when we get 8 over 1 times 2 over 1, we end up with 16. Okay? So when x is equal to 1/2, y is going to be equal to 16. Then 8 divided by 1 is going to be 8. 8 divided by 2 is going to be 4. And 8 divided by 4 is going to be 2. Now, what I could do here is, since I've got this 16, which is going to be way off my graph, what I could do is I could add in an 8 right here, and 8 divided by 8 is going to be 1. So instead of doing 1/2 and 16, I can do 8 and 1 instead, which is going to fit more precisely or a little bit better on the graph. I'm also going to get rid of the -1/2 then, because it's going to have the same issue as this one did. It would end up just being -16. So I'm going to put in a -8 down here. So 8 divided by -1 is -8. 8 divided by -2 is -4. 8 divided by -4 is -2. And 8 divided by -8 is -1. So now now that I've got all these points, I can go ahead and plot them. And so I'm looking at 1 and 8. So 1, and then I don't have this marked off real well, but I've got 2, 3, 4, 5, 6, 7, 8. And then 2 and 4. So it's going to be right about there. Then you've got 4 and 2. So that's going to go there. And then 8 and 1. So 1, 2, 3, 4, 5, 6, 7, 8. And a 1 there. And what we can see just from the shape of the first half of the graph is that when we have a stretch, or what we would consider a stretch with any other sort of vertex form, what that's going to do is it's going to pull the graph away from the origin, or it's going to pull the graph away from the intersection of the asymptotes. We'll see the exact same thing happen over here. So when we go over here, we've got -1 and -8. So that would be right about there. Then we've got -2 and -4, which is going to be there. -4 and -2. And then -8 and -1. And again, what you can see happening is the graph, when that a value is greater than 1, is going to get pulled away from the intersection of the asymptotes. And that's it for that problem. For problem number 2, we're being asked, what is the effect of a equals 6, 0.25, and -6 on the graph? So again, here we have our parent function, and we're going to see what is the relationship between the a value and that parent function. Now, what we saw in the last problem that we did was that when a was equal to 8, the graph got pulled away from the origin, or it got pulled away from the intersection of the asymptotes. So we should expect to see that here as well. With a equal to 6, we're going to see something that looks along the lines of this, where a is going to again get pulled away from the intersection of the asymptotes, and it's going to happen down here as well. By the way, these two will be mirror images of each other across y equals -x. Then for 0.25, since 0.25 is less than 1, what we can expect to see is that this graph is going to get pulled down towards the intersection of the asymptotes. So you're going to see a graph that looks more like this. It's not going to be quite as rounded, and it's going to get much, much closer to the intersection of the asymptotes. Then if we have a equals -6, this negative means that it's going to reflect, you can call it either across the y-axis or across the x-axis. It doesn't really matter because these are mirror images of each other anyways. So if we have -6, it's going to look like this, but instead of being in the first quadrant and the third quadrant, it's going to be in the second quadrant and the fourth quadrant. So it will end up looking like this. And that's the effect that the A value has on rational graphs. Right, so in problem number 3, we're going to look at what is the graph of y equals 1 over x plus 1 minus 2. Now to do this, what we're going to do is we're going to fill out this list of items that is going to make it easier for us to actually get to the graph. And by get to the graph, I mean to fill out our XY chart. So we're going to start with the A value. Now you should recognize this from all the other things that we've done so far, quadratics, absolute values, back in Algebra 1 when we did exponentials and radicals as well. So the A value again tells us stretch, compress, reflect. And since the A value is 1, that means that we don't have any stretch, compress, reflect. So I'm just going to write in none. Then we're going to look at the H value. Remember that the H value is in this position here on a rational function. So we're always going to go the opposite of what we see. So since we see x plus 1, we're going to make this -1. So the H value we're going to write is -1. Now the reason why this is important, the reason why we want to know this, is because this tells us where our vertical asymptote is. So the H value is going to tell us that the vertical asymptote is at x equals -1. Now this line that I've drawn here on the XY chart, that represents the asymptote. That's the point or the line where our graphs cannot touch and cannot cross. So I'm just going to go ahead and draw in a -1 right there, and then I'm going to come over to the graph and go ahead and draw in my dashed line to indicate that that's where my vertical asymptote is. Next I'm going to look for the K value. The K value is -2. And that K value is then going to tell me that the horizontal asymptote is at y equals -2. So again, what I'm going to do is come over here, go to y equals -2, and I'm going to draw in that horizontal asymptote at -2. So again, with my graph, when I do this, my graph cannot touch these asymptotes. So they're going to continue getting closer and closer and closer. So it'll go maybe like 1/2, 1/4, 1/8, 1/16, 1/32, but it's never ever going to get to that asymptote. It's always going to stay above it or below it, to the left or to the right, depending on if we're talking about a horizontal or vertical. Now the intersection of the asymptotes is at -1, -2. And the reason why this point is important is because what's going to happen is the parent function, the intersection is at 0, 0. And so we would always have our graphs either in 1 and 3, or we would have our graphs in quadrants 2 and 4. What this does is it basically moves those quadrants, it kind of moves those quadrants down. It's not that it's taking negative numbers and making them positive, or positive numbers and making them negative. All we're doing is we're visualizing how that parent function could be moved. And that's what those vertical asymptotes are doing, and that's what the intersection does for us. Now, I'll come back to the domain and the range in just a little bit. So what I want to do is I want to start figuring out what are some points that I can use in order to be able to graph this. So seeing that this is not a reflection, because this is a +1, that tells me that my graph is going to be here and here, and what would have been quadrants 1 and 3. So what I'm going to do is I'm going to look at what are 4 values that are greater than x equals -1, and what are 4 values that are less than x equals -1. So I'm going to go with, let's see, we'll go with -1/2, and 0 and 1 and 2. And then down here, I'm going to go with negative 3 halves, and then negative 2, negative 3, and negative 4. So by doing this, what I'm going to do now is I'm going to take all of these values that I just listed out here, plug them into the original equation, and find out what is the value of y. Now, again, the one value you're not allowed to have, the x equals negative 1, why can't we have negative 1? Because if we put negative 1 in for x, then we get negative 1 plus 1 is 0, and so we'd end up with 0 in the denominator, which is undefined. We can't have 0 there. So that's why we have this vertical asymptote. It's telling us that our solution or our x value cannot be negative 1 because it would make the denominator undefined. So let's go ahead and put 2 in. So if you put 2 in, you get 1 over 2 plus 1. So 1 over 3 minus 2. So 1 over 3 minus 2 is negative 1 and 2/3. And so negative 1 and 2/3, or you could write this out as 3 negative 5 over 3. Whichever you prefer, you can do. I would just stay away from decimals if possible, because they're not, like with this one, you're going to end up with something that's repeating, and it's just easier to deal with the fractions. You don't have to do any conversion of it either. Now the next one, we'll plug 1 in, so 1 over 1 plus 1, so 1 over 2 minus 2, so negative 1 and a half, or negative 3 over 2. Plug in 0, so 1 over 1 is 1, minus 2 is negative 1, and negative 1/2, so 1 over negative 1/2 plus 1. So 1 over 1/2 is the same thing as 2, so 2 minus 2 is 0. If you need to, work it out, set it up as a complex fraction, change it into a horizontal division problem, and then work it on out. Then, negative 3 halves. So again, this is where we're getting into a little bit more difficult territory here, especially when you're trying to do this mentally. So negative 3 halves plus 1, so negative 3 halves plus 2 over 2, so negative 1/2. 1 over negative 1/2 is negative 2, so negative 2 minus 2 is negative 4, and hopefully this is going to work out. We'll see if it does when we actually go to graph it. Then we've got negative 2, so 1 over negative 2 plus 1, so 1 over negative 1 is negative 1, so that gives us negative 3 when we subtract 2. Then 1 over negative 3 plus 1, so 1 over negative 2. So you get negative 1/2 minus 2, so you get negative 2.5. And then that would give us negative 5 over 2. And then for negative 4, 1 over negative 4 plus 1. Negative 4 plus 1 is negative 3, so negative 1/3. So negative 2 and 1/3, or 6, 7, negative 7 over 3. Okay. Now that we've got our 4 points here, our 4 points here, we're going to take it over to the graph, and we will put this onto the graph. So we've got 2, and then negative 1 and 2/3. So 2 and negative 1 and 2/3 is going to be right about there. Then 1 and negative 1.5 is going to be right about there. 0 and negative 1 is here, and negative 1/2 and 0 is there. So you can see that on the right side of our graph, it's going to end up looking like this. So if we've done this correctly, what we get down here should mirror this exactly across, well, what would have been y equals negative x, but now it's been moved down. So the next thing we've got is negative 3 halves, or negative 1.5 and negative 4. So negative 1.5, and 1, 2, 3, 4. And then negative 2 and negative 3. And then negative 3 and negative 2.5. And finally negative 4 and negative 2 and 1/3. And you can see that again, we do have that mirroring that's taking place, and our graphs never touch or cross that asymptote. So this would be the correct solution here. So go ahead and take a look at got it number 3 and see if you can do got it number 3 on your own. All right, the last problem that we're going to look at in this section is problem number 4. And we're asked, what is the full equation for y equals 2 over x based on the given graph? So really the hard part has been taken care of for us, and that is already telling us that the a value is 2. Otherwise we'd have to calculate that, and that's a little bit of a messy thing. All we really need to do is find out what is the h value and what is the k value, and then plug those in here. So what we're going to do is go over to the graph, and we're going to find out where does the vertical asymptote go through the x-axis. So you can see that the vertical asymptote goes through the x-axis at x equals -3. Then we're going to say, where does the horizontal asymptote go through the y-axis? And if we count it up, we get 1, 2, 3, and 4. So we get y equals 4. So our h value is -3, and our k value is 4. So we go over here, plug those into our equation. So y equals 2 over x minus -3. And then we're going to add 4 to that. So then go ahead and simplify this down. Y equals 2 over x plus 3 plus 4. And that's how you solve that problem. So go ahead and take again, look again at got number 4 and see if you can do that on your own.